all the dignitaries and participants to the third lecture in the national level lecture series on mathematics. We have called distinguished academician for this lecture series. For today's lecture, we have the eminent personality in mathematics, Dr. D.D. Pawar sir, Chairman, BOS in Mathematics, Swami Ramanand Tirth, Marathwada University, Nanded. Pawar sir deserves a special thanks for all his support and encouragement to our activities. Pawar sir has a busy schedule. He will continuously give constant to our request. His dedications to students has helped us in all our functions. I am well assured that our sir lecture will be path-breaking for students and teachers. You will definitely enjoy this lecture. The chairperson of this session, well-known academician, Dr. B.D. Karande sir, Academic Council member, Swami Ramanand Tirth, Marathwada University, Nanded. He is also associate professor and head departments of mathematics, Maharashtra Udayagiri College, Udgir. Also deserve a word of thanks for his motivating presence. Thank you very much, sir. Now I request to Karande sir, please start the session.
Okay, sir. On the occasion of 75th Azadi Ka Amrit Mahotsav, Department of Mathematics, Digambar Bindu, ACS College, Bhokar, organized a one-week national lecture series on mathematics. Today's third day of this series. Convener of this program, Dr. S.B. Chauhan sir, co-convener Dr. A.B. Chauhan sir, organizer secretary Prashant Takke sir and R.A. Hoge sir. I welcome you all in this lecture series. As a chairperson, I am very much thankful to the organizers of this one-week national level lecture series. Today's resource person, Professor Dr. D.D. Pawar sir, as a BOS chairman in mathematics, also director School of Mathematical Sciences, and his topic is linear algebra. First of all, may I request the Professor Dr. D.D. Pawar sir to present our idea on the topic linear algebra. Sir, please.
Okay, sir. Thank you. Good evening, one and all. Just a minute. I am Professor D.D. Pawar. Initially, I was planned a lecture on very high level linear algebra, but I have taken some inputs from Professor Chauhan and other faculty members. Many students are from BSc as well as those are from PG, but they are external member of post-graduation. That's why I have replanned my talk, and I am giving talk on very basic fundamental ideas about the linear algebra. Okay. We know that linear algebra basically divides, it has main contain, that it depends on the vector space, linear transformation and its properties, matrices and their properties, diagonalizability and canonical forms, inner product spaces, and normal form and quadratic forms. Actually, I want to talk about different canonical forms and Jordan canonical forms, but there is a need of all the basic concept for that forms. So I avoid that topic and now come to the very basic thing from the definition of vector space. Now I am going to talk about the definition of vector space. Before going to talk about the vector space, first of all, I want to compare you the basic difference, fundamental difference between the definition of group, ring, and vector spaces. These are the different algebraic structures. What are the basic difference in between that all the algebraic structure, group, ring, vector space, modules, all those things? Actually, if we observe the development of all that algebraic structure, there is very slight difference. There is no need to remember all those things. There is no need to mug up all those things. If you will understand all the concept and what is the difference, how the construction of all that definitions, then you can easily remember all those things and you can easily reproduce all those things. It is not very much difficult task. I think yesterday there was a lecture on abstract algebra from Dr. Nitin Dakunde sir. He has explained about the group theory, but a little bit I will talk about the very basic things about the group theory, as well as first definition is group. Then I want to talk about ring, and next is vector spaces. Okay. We know that the definition of the group, either ring or vector spaces, it is defined on a non-empty set. Okay, let it be denoted by here G. G be a non-empty set together with some binary operation. Together with some binary operation means if we want to do something, this non-empty set satisfying some property with the help of some binary operation. Operations means it provides some tool for doing or providing doing that properties. That tools we call as the binary operations. These G's, either group having the binary operation plus, we say that G is a group with respect to addition, or G star or dot. G is a group with respect to multiplication. This group G not satisfy both the binary operation, are not taken together both the binary operation addition and multiplication. They have taken one at a time, either addition or multiplication. But in terms of the ring, if we talk about the ring, if we say that R be a non-empty set together with the binary operation, here the binary operations are R plus and dot. R plus and dot means a ring is defined with the help of these two binary operations taken together. Means ring satisfies their properties with the help of these two binary operations. But as far as the group is concerned, we will take either addition or multiplication. And if we talk about the vector space V, it will take two binary operations, addition and scalar multiplication. We can say that addition and scalar multiplication. Addition and scalar multiplication, addition is as usual. We can say that V plus, but the scalar multiplication will not define like that dot or star or like that. Means we will directly multiply with some scalar to the vector. Okay, these are the basic binary operations for the group, ring, and vector spaces. Now, if we talk about the definition, now this definition, if we say that first, if we talk about this group with respect to addition, we know that the properties are common. First property, that is a closure property. Second one is the associativity. And third one is identity. And fourth one is inverse. These four properties will satisfy either with respect to addition, then we can say that the group is with respect to the addition. If this property will satisfy with respect to the multiplication, then we say that this non-empty set is a group with respect to multiplication. I think all of you familiar all these properties. Yesterday, Dr. Dakunde talked about all those properties. I am not going into the details, but these properties are completely, if we talk with respect to addition, then all these operations we will take with respect to plus, and here we will take with respect to dot or multiplication. Now, next algebraic structure is the structure of ring. The structure of ring, the first important property is R plus is an abelian group. Is an abelian group. Abelian group means it is grouped together with the commutative property. That proper group is called as the abelian group. Means one extra property is there. Means all these four properties with respect to the addition is already included in the ring. See that this structure included all the properties of a group with respect to the addition. There is one extra property is there, added a commutative property is there. This R plus is an abelian group with respect to am I audible now? Current sir?
Yes, sir, poor sir.
Okay. R plus is an abelian group, means together with the properties of group with respect to addition, there is one extra property is there, that is a commutative property. And all of you very well known about the commutativity. Commutative property with respect to addition, if we take two elements from R, A comma B belongs to R, then the commutativity means A plus B can be written as B plus A. This is the property of commutative. Means R plus is an abelian group already include this property. Means naturally we can say that ring is a group with respect to addition. Always I talk about with respect to the addition, not multiplication. And the remaining second property is about the properties of with respect to multiplication. Properties with respect to multiplication. Now second property is in the second, suppose we can say that there is a first property, distributive property. Distributive property means left distributive and right distributive. If we say that A, B and C, these are the three elements from the ring R, then the distributive property with respect to multiplication, A dot B dot C is equal to, oh sorry, distributive property is there, A dot B plus C is equal to AB dot AB plus AC. This is the left distribution. Means A is left distributive over B and C. And similarly, the second distributive property, right distributive property, is that if we say A plus B dot C can be written as AC dot BC. This is the second property, this distributive property. Now, the second property with respect to the multiplication is associativity. Associative property. Associativity with respect to multiplication. This is with respect to multiplication. Also, all of you known about this associativity property. Yesterday, Dr. Dakunde was talking about this property. This similar same property with respect to multiplication is here. Next, and the one of the important properties, associativity, distributivity is there. And if we say that if the unit element is there, then the ring is called as the ring with unity. If all those properties satisfied by the non-empty set G together with the two binary operation addition and multiplication, then we say that it is a ring. Okay, see that all those properties already included in the ring. Now we talk about the vector space. Means there are some two properties are there that are not included in the definition of ring with respect to multiplication. One is identity and another is the inverse. Multiplicative inverse is not exist in ring, as well as multiplicative identity is not exist in the definition of ring. They are separately defined. Ring with unity, or we can say that a non-empty non-zero element has a multiplicative inverse, then that ring is called as the commutative ring is called as the field. Means another definition is there, including the inverse. Okay, In the definition of vector space, again, same kind of first property is there, that V plus is an abelian group. Is an abelian group. See that? All the definition having the first property with respect to the group means group structure is included in the definition of ring as well as in the definition of vector space. V plus is an abelian group. And the next properties, just like as previous definition of ring, next properties are with respect to the scalar multiplication. Here we talk about the scalars and vectors, because vector space is defined on the scalars and vector. That's why always we talk about V be the vector space over the field of something real number, over the field of complex number, means we always define the vector space over the field, which field will be there. And just now I was talking about the definition of field. Field is nothing but the commutative ring in which every non-zero element has the multiplicative inverse. Means all the properties of commutative ring together with multiplicative inverse, that kind of ring is called as the field. And vector space is defined always over the field. Which kind of field we have taken for the scalar quantities. Second property, there is a first property in the second. All these properties, second properties, are related with respect to the scalar multiplication. Here again the distributive property is there, distribution is there, scalar. Suppose we say that alpha be the scalar over the field F, and U and V are the two vectors from the vector space V. We say that the scalar alpha is distributed over the addition of the vector. So alpha U plus alpha V. This is the left distributive law. But this left distributive law is scalar is distributed over the addition of vectors. And the second distributive law is equal to alpha U plus beta U. Means this vector is right distributed over the addition of two scalars. This is the distributive property with respect to addition and scalar multiplication. Second is again associativity, but this associativity is different than the previous two, because associative law is with respect to the scalars and vectors. Alpha beta into U is equal to alpha into beta U, or that can be written as beta times alpha. This is the associative property with respect to this alpha and beta. Are the two scalars and U be the vector. Hello, please unmute your mute your mics. And one of the third important property is 1 into U is equal to U, where U belongs to the vector space. If the space satisfying all those property together with these two binary operation, that space is called as the vector space. If the field is real, then we say that real vector space. If the field is complex, then we say that that space is the complex vector space. Means if we observe all these three algebraic structure, then we confirm that all the definitions are prepared are based actually on their respective binary operation. Either if we say that about the group, about the ring, about the vector space, all these definition, all these property depends on their respective binary operation. If you know the basic things about the binary operation, no need to remember all those things. Just you know that what kind of operations are there and what kind of properties are there. All these properties will satisfy by their respective structures. Then we say that either it will be group or ring or vector space. Okay. Same way, you can define the subgroup, subring or subspaces. Same kind of definition. No need to remember. Same kind of structures are there. Same kind of technique to define all those definitions. If we talk about the subgroup, This is next is subring. Actually, fourth one is the module. Module is also defined on the same technique, with the help of same technique. Next is subspace. You know that subgroup. Subgroup is defined as, if we say that S is a non-empty subset of the group G. It is a non-empty subset of a group G. We say that S is a subgroup of G if S is itself a group under the same binary operations of G. Means S will satisfy all the properties of a group. S is itself a group. Itself a group with same binary operation. With same binary operations of G. Okay. A non-empty subset of a group G is called as a subgroup if S is itself a group with the same binary operations of G. So extend same definition for subring also, for same definition for subspace also. Means subring means what? If we say that S is a non-empty subset of a ring R, is called as a subring of R if S is itself a ring with the same binary operations of ring R. Same kind of exactly same definition, no change at all. Only here we say that it is a group, here we say that it is a ring. Same binary operation of a group G, it is again a same binary operation of a ring R. Same definition we will extend for the subspace. Same kind of technique, same kind of definition. Means we say that suppose S is a subspace of a non-empty subset of a vector space V over the field F. V is a vector space over the field of F. S is called as a subspace if S is itself a vector space over the field of F. Say that subgroup, subring, subspace has exactly similar structure. Only their definitions are respective changes are there only because of their respective group, respective ring, and respective vector space. Okay, and all these depends on their binary operations again. It will satisfy the same binary operation. If we observe some results about the subgroup, subring, and subspaces, if we talk about the intersection of two subgroups, will be subgroup or not? Intersection of two subring, intersection of two subspaces, or just like as intersection, if we talk about the subspaces, union of subgroup, subring, and subspaces also, we got the same technique or same kind of results we will obtain. If we talk about the intersection, let's suppose that S and T are the two subgroups of G. What about the intersection? That S intersection G is naturally again a subgroup of G. Means intersection of two subgroups will be the subgroup of G. Same result, same proof. I am talking not only about the statement, but I am talking about the proof also. In the proof, if we talk about proving the result of subgroup of G, the proof will be similar way. Only just proving the binary operations. Here about the subring, same thing, same kind of results are there because first property of ring is R plus is an abelian group. R plus is an abelian group. So naturally, if it is a subgroup in G, then it will be again a subring in G. That's why same kind of result will be true for S intersection G is, sorry, S intersection, not G, it is T. S intersection T is subring of R. Again, same proof, same kind of result will be true for the subspace. Means intersection of two subspaces will be again a subspace of vector space V. And if we see the proofs or techniques of proving the subgroup, subring, and subspaces, that will be again depends on their binary operation, respective binary operation. How it is? There is some theorems are there. That theorems are subgroup if and only if S is subgroup of G if and only if. What are the two basic properties of binary operation of group? Either plus or multiplication. So naturally here S is a subgroup of G. If we want to prove that S is a subgroup of G, then with respect to addition, that property will be A minus B again belongs to the G for, sorry, S for A comma B belongs to S. With this property, see that the closure property is there and inverse property is there. Means two binary operation will be included in the definition of subgroup. This is the shortcut. This is the test for subgroup. If S is a subgroup of G, then if it satisfies this property, A minus B belongs to S, then we can say that S is. I'm talking about with respect to the addition. If we talk about with respect to the multiplication, same property we can express in the form of closure property, means A into B. Again, the inverse property will be included in the same statement. A into B inverse belongs to S, then we can say that then S is a subgroup of the group G. This is the shortcut, or this is the test for the subgroup. Same kind of technique we will use for proving the subgroup. Same kind of statement will be there. Same kind of technique will be there. No need to every time prove that all those properties of ring, all those properties of group, all those properties of subspace, because the definition says that it is itself a group, itself a ring, or itself a vector space. Then that kind of subset called as a group, subgroup, subring, or subspace respectively. Okay, and every time proving all those properties, it is difficult task. That's why this test provides us the shortcut. With this shortcut, easily we will prove the results. Okay, either this or this. This is with respect to multiplication. This is with respect to addition. If we talk about the subring, then subring, you know that two binary operations are compulsory, because R is the ring with respect to addition and multiplication. So naturally, for proving the subring, we need the two binary operation. For the subring, two binary operation means if and only if that first binary operation is addition, means A minus B belongs to S. Inverse property is not included in multiplicative inverse is not in the definition of ring. So just like as this, the multiplicative inverse is not there, but additive inverse will be included in the definition of subring. Next property is multiplicative property. A dot B belongs to S, for A and B belongs to S. If these two properties are satisfied, this is with respect to the addition and this is with respect to the multiplication. These two binary operations are there in the test of subring. If these two conditions will be satisfied by the any non-empty subset, then directly we can say that that subset is called as the subring of the ring R. No need to prove all those properties of subring, 8 to 9 properties of subring. Okay. Similarly, if we talk about the subspace, next theorem is about the subspace. S is subspace of the vector space. Subspace of P of F, if and only if, the shortcut way is if and only if alpha U plus beta V belongs to S, where U and V belongs to S and alpha comma beta belongs to F. Here see that this is the scalar multiplication and this addition represent the one binary operation, that is addition, and this multiplication alpha U, either we talk about alpha U or talk about the beta U, this represent the scalar multiplication. Means again there is a role of binary operation, means this test will again depends on the property. If we say that S plus and dot, these two binary operation, plus is there, dot is there, this plus operation is there, dot operation is there, there is a dot operation. In short, if we prove only this condition, alpha U into beta V belongs to S, then we can say that S is a subspace of the vector space V. Means only you know the binary operation how to imply that binary operation on that particular kind of algebraic structure, then easily you can remember, you can construct the definitions of group, ring, vector space, and their subgroup, subring, and subspaces also. Again, I was talking about the intersection of two subgroup. Again, as intersection of two subgroup is again a subgroup, is again a subring, is again a subspace. Next, what's about the union? Union of two subgroup, it will be a subgroup or not? Will be a subring or not? Union of two subspaces will be a subspace or not? It is need not be true for all these three. For all these three structure, S union T is need not be subgroup, subring, and subspace. Say that. Means those things are satisfied for the subgroup, that will be again same kind of structure, same kind of definition will be satisfied for subring, also for subspace, also for submodule. Means fourth structure is for module. Module is also having the same kind of extension, same kind of definition will define. So union, if we see the particular kind of examples for this, because need not means it is not always. Sometimes it will satisfy. Sometimes yes union T will be a subgroup. Sometimes yes union T will be a subring, will be a subspace, but it will not always. Just like as intersection. Intersection of two subgroup will always subgroup. There is no doubt at all. But sometimes union will be sometimes, but sometimes not. For the such kind of results, there is a need of giving some counter examples. How to prove that union? You can prove that when it will not a subgroup, it will not a subring, it will not a subspace. Easily you can prove that results. If we take, for example, suppose S is equal to multiples of 2n. Okay. N belongs to Z. It is a subgroup because set of all integer with respect to addition forms a group. Okay. And 2n, multiples of 2n means even integer. It is a set of even integers. And suppose T is equal to multiples of 4n, suppose. Even integers or odd integers also, that will it is not odd integer, it is again set of even integer plus multiples of 4. Okay. If we take any element from 2, suppose or if we take another example, suppose S is equal to A0. So that A belongs to and T belongs to 0B. Okay. And addition of this A plus B, these two elements, A plus 0B, it is equal to AB, and that is not belongs to the union of this, because AB is not either in S or not in T. Means if we construct the example, different examples for the subspace, subgroup, or subring, such kind of things is happen. Same kind of, because if it is not a subgroup with respect to addition, then same example we will extend for the subring, because first condition of ring is R plus is an abelian group. If it is not a subgroup, union of two subgroup will not a subgroup, then naturally union of two subring will not be a subring, because first property will not hold here. Same thing is happen with subspace. Union of two subspaces will not be a subspace because first property is V plus is an abelian group. That's why this example will sufficient for the proving union of two subgroup, two subspaces will not again form a subgroup of subspaces respectively. Okay, means you study comparatively all the structure at a time, then easily you can understood all those differences in between their definitions. Now next, not only this definition, but so many theorem also. So many theorems from the group, from the vector space, from the rings having the same kind of statement, same kind of proofs also. Only your comparative study will be important. If we go to the definition of suppose homomorphism, can you want some examples about the subgroup, subring, subspaces? How to prove it? Or later on we will discuss on it. When it will not, it will be. Later on we will discuss on it. If we define the map in between the group G and G dash, if we'll define the map in between G and G dash, where G is a group, G and G dash both are the group with respect to something. Because if we define the homomorphism, definition of homomorphism, homomorphism on the group. If we define the definition of homomorphism, it has the different forms of the definition. Many times students will confuse about this definition because in the books, the definition of homomorphism is defined with respect to the both G and G dash with respect to the groups, with respect to the binary operation multiplication, or either with respect to the addition. But if I say that if G is a group with respect to addition and G dash is a group with respect to multiplication, definitely student will confuse about the definition of homomorphism. They will not able to define the definition of homomorphism. So first understand their binary operation, then easily you can define their homomorphism. There is no need to remember all those definitions. There are, see that if we talk about, there are four kinds of possibility for G and G dash. If G is with respect to multiplication, G dash is a group also with respect to multiplication. Second possibility is the group G is with respect to addition. G dash is a group with respect to multiplication. G is a group with respect to multiplication. G dash is a group with respect to addition. And G is a group with respect to multiplication. G dash is also a group with respect to multiplication. Means for this homomorphism, for this map, there are four kind of possibilities of their respective binary operations. So the definition of homomorphism definitely defined with four kind of different forms of their definition. Student either observe the definition of first this, either this or last one. Some of the books define the definition of homomorphism with respect to multiplication or with respect to addition. Students actually not familiar with this structure, and many times they will confuse with this kind of definition. So I am going to define the definition of homomorphism about the first structure. First structure means G. Domain group G is with respect to addition. Domain codomain group G dash is with respect to again addition. At that time, the definition of homomorphism will be defined as f of a plus b is equal to f of a plus f of b. This is simple definition of, repeat, I will give the numbers. First structure is denoted by first, second is second, this is third, and this is fourth structure. For the first structure, your definition will be domain. See that this binary operation represent the domain G, and this binary operation represent the codomain G dash. That's why our structure is F, a mapping F is the homomorphism from the group G to G dash, where G and G dash are the group with respect to addition. At that time, your definition will be in this one. But if we talk about the second structure, your mapping is defined on G. G is with respect to addition, and codomain G dash. The group G dash is the with respect to multiplication. If we talk about the second, your definition will be defined as f of a plus b is equal to f of a into f of b. Means second structure. This is the second structure, and the definition of homomorphism is defined in this way. If we talk about the third one, the definition will be defined in the form of a dot b is equal to f of a plus f of b. And if we talk about the fourth structure is defined as f of a dot b is equal to f of a into f of b. Say that means depends on the respective binary operation, your definition of homomorphism will have the different forms. And naturally, these two forms will not given in the definitions of books. Many authors will not define your definition in the form of these two forms. Only either you can observe the definition in the form of first or in the form of fourth. Okay. Same way, if you will understand these all those structures, all these definition with respect to their binary operation easily, you can yourself define the definition of homomorphism defined on the ring. F is from R to R dash. No need to remember this definition because we know that the ring R as well as R dash both are having compulsorily both the binary operation, addition and multiplication, as well as addition and multiplication. Okay, that's why your homomorphism will taken together these two binary operation. Definition of homomorphism for the rings is define these two binary operation at a time. Okay, so your definition will be f of a plus b is equal to f of a plus f of b. This is for binary operation from domain, and this is the binary operation for codomain. This is the first property, and second property f of a into b is equal to f of a into f of b. You see that these two properties combinedly taken together for the definition of homomorphism over the rings. But for the group, you can take any one, either these or these or these or this. Any one will define the definition of homomorphism. For the ring, these two properties will be compulsorily define the homomorphism. Okay. No need to remember. Only you know that the binary operation, you can easily define the definition of homomorphism. Okay. Next, we are going to define the homomorphism over the vector space V and V dash, where V is the vector, V and V dash both are the vector spaces over the field F. Now we are going to define the homomorphism. We are going to define the homomorphism, but we call that homomorphism are called as the linear transformation. There is a new name why we called it as a linear transformation, because we observe all those linear properties in the vector space. So that homomorphism here we called as a linear transformation. Again, now you know that which are the binary operation for the vector space V as well as vector space V dash. Here, one is the addition and another is the scalar multiplication. Same binary operations are satisfied by V dash. So just like as the ring, your homomorphism or your linear transformation will satisfy both the properties at a time. Then and then your definition will form. Either you can take separately these two binary operation, or combinedly you can take both the binary operation. Separately means first you can use binary operation addition, means first property is f of a plus b is equal to f of a plus f of b. And second property is with respect to the scalar multiplication. Just like as previously in the ring, there is a simple kind of multiplication in between the two elements of the ring. But here in between the vectors and scalar. The second property is with respect to the scalar multiplication. Alpha A is equal to alpha times f of A, where alpha belongs to the field F and A and B belongs to the vector space V. Okay, this binary operation is belongs to the domain, and this binary operation is belongs to the codomain V dash. See the difference in between all those definitions. Easily you can define your definition with the help of your binary operations. Okay. Not only this, but also in the definition of isomorphism. Same kind of definition is defined with the help of this structure. Definition of isomorphism is exactly same for the group, for the ring, and for the vector space also. A homomorphism from G to G dash is called as the isomorphism if it is 1, 1 as well as onto map. That map is 1, 1 and onto. Then we can say that that map is an isomorphism. Same definition will satisfy for the ring as well as for the vector space. Means here we can say that for the vector space we can say that isomorphism means a linear transformation from two vector spaces V to V dash is called as an isomorphism if and only if it is 1, 1 as well as onto. Okay. Again, there is different definition of kernels. Kernel of F, kernel of the vectors, for the F is a homomorphism. We will define the kernel of the homomorphism F for the group, for the ring, for the vector space. Again, if we observe the definition of kernel, same kind of structure is there, same kind of idea of defining the kernel is there. No need to remember. If you know the one definition, their respective binary operation, then easily you can define all those definitions. So kernel of F over the group G G to G dash. If we talk about R to R dash and vector space V to V dash, that kernel is defined and denoted as kernel of F is defined set of those elements from the group G. Actually here G and G dash. If we say that G and G dash both are the groups with respect to suppose multiplication or addition, both are having, if we talk about both are the groups with respect to either addition, it is compulsory, or with respect to the multiplication. So if we say that suppose A belongs to G such that F of E is equal to E dash. If G and G dash both are the groups with respect to the addition, then this E is the additive identity from G. This E dash is the additive identity from the G dash. If we say that G is a group with respect to multiplication, this is with respect to addition, then this identity is with respect to additive identity means 0. This is multiplicative identity means 1. That's why this structure is defined in terms of identity, because the value of identity depends on the with respect to the G with respect to the G dash. Same definition we will define for the ring. For the ring, kernel of F is defined as for every element in R, because here only there is additive identity. No multiplicative identity will be exist in R and R dash. That's why there is no question about the multiplicative identity. So additive identity will be exist also for every element X belongs to R such that F of X is equal to 0. F of X is equal to 0. This definition means every element is mapped to the 0 identity element. Or we can say that 0. We can say that it is E, that it has the exact limit. Same definition we will define for the vector space also. Every element from the domain map with the 0 element from codomain means F of X is equal to 0. That is the definition of kernel of the vector space linear transformation over the vector space V and V dash. Means again the structure of definition, all those definitions are exactly similar. Again, I have observed one result. That result, all of you are already familiar with that result, that kernel of F. Kernel of F is equal to singleton 0 or singleton 0, we can say that identity, additive identity, if and only if F is 1, 1. Same result will be true for the group, for the ring, for the vector space. Same kind of proof will be there. Means exactly the technique of proof is again similar for proving all those results. Means today's my lecture is only devoted on the topic of comparison in between the different algebraic structure. If we talk about the algebraic structure of group, ring, and vector space modules, comparatively you will go through the definitions, go through their respective theorems, their subspaces, their homomorphism, all those. There are so many theorems are there having same technique, same proof, same counter examples. There is slight extension because of their respective binary operations are there. So you will go through such kind of technique. You definitely don't bother about all those definitions. You easily define all those definitions with the help of their respective binary operation. So with this few words, I stop here because now, because of time constraint, I will not talk about the linear transformations and linear independence, dependence, all those things. I stop here. Thank you. Any questions?
Session is open for the question answers. Please the questions from the students. Sir, one question from one student. What is the prime ideal?
What is prime ideal? First of all, ideal, that student must know about the ideal. Ideal is related with the ring. Ideal satisfies some properties. That one is the property of that scalar multiplication and closure property. Closure property and inverse is there. Then that is called as the ideal. And prime ideal means that element should be primes.
Prime number. Any question from students and faculty members? No any questions. Dr. D.D. Pawar sir, our presentation is very nice, excellent. It will be useful for all participants, our presentations. You present a comparative study for the group, linear group, ring, vector, space, field, so many definitions and theorems. Thank you, sir. Lastly, thanks to the convener, Dr. Chauhan sir, for inviting me as a chairperson of these sessions. Thank you very much. Thanks.
Actually,
Hello.
just a minute, sir. Actually, for the student, I'm talking about all this comparison because from last some years, I have not taught modern algebra, ring, group, and all those things. But I know all those things. No need to remember all those definitions. No need to go again and read all those definitions. But I know the structure. I'm easily going to define, and every time it is in my mind that what is the structure of group, what is the structure of ring, what is the structure of subspace, all those things. That's why there is no need to remember all those things. All those things always with me because of the understanding and because of the comparison. So student will take benefit in their exam also with this technique. Okay, sir.
In this presentation, one idea is clear for all students, sir. The homomorphism from F from G to G dash. That is the plus dot plus dot. This is the clear idea, sir.
Yeah, there is a big confusion in between the student because of the definition of homomorphism.
Yes. Very nice.
Hello.
Yes, sir. Wow, Chauhan sir.
टाके सर.
Okay, हा बोला.
हे करा ना सर. good.
Hmm?
Huh.
Vote of
Oh,
thanks.
vote of
Okay.
thanks.
Thank you, sir. As it is a formality, I have to express the vote of thanks. But we are always thankful, and we would like always remain grateful to Dr. D.D. Pawar sir, Dr. Karande sir for all their support to our institution, to Dr. S.B. Chauhan sir. Today's lecture, do not belong to the field of mathematics, but I am seeing so much positive responses, and the fluency that Pawar sir's lecture was going through defines that how helpful it was. Once again, I express my sincere thanks to Dr. D.D. Pawar sir, Chairman BOS in Mathematics, and the chairperson of the session, Dr. B.D. Karande sir, and on the behalf of, with the permission of the organizers, declare that this session concludes here. We will meet tomorrow on the same time. So students will join on the same time.
Okay,
Thank you, sir. Thank you very much. Students are requested tomorrow's lecture.
Karande sir.
पवार सर हा सर
हा चव्हाण सर.
हा सर.
संध्याकाळी
Thank you very
संध्याकाळी
much.
आता डिपार्टमेंटला बसवलं, आता जेवायचे घरी काय येऊ देणार आहेत का? व्यवस्था करावं लागेल ना, असं कसं? हा, सकाळी 10 वाजेपासून 8 वाजेपर्यंत बसवलं तुम्ही. हा,
नांदेडला कधी आल्यावर हे करतील हो.
ओके सर, ओके, थँक्यू.
पवार
Okay,
सर
sir.
ते
Thank you, Karande
विद्यार्थ्यांचं
sir, Pawar sir. Thank you.
ओके पवार सर
हा
Thank you,
सर.
both of you.
विद्यार्थ्यांची एक रिक्वेस्ट आहे, आताचं प्रेझेंटेशनचं पीडीएफ जर ग्रुपवर टाकलं तर बरं होईल असं विद्यार्थ्यांचे कॉमेंट्स आहे.
हे तर पीडीएफ नाही, मी रायटिंग तुमच्या समोरच राईट केलंय.
रायटिंग मध्ये म्हणजे पूर्ण होत नाही का पीडीएफ मध्ये कन्वर्ट?
बघतो, पीडीएफ झालं तर पाठवतो, काय अडचण नाही.
हा बघा, म्हणजे थोडं म्हणजे आयडियल खूप चांगलं, म्हणजे पॅरलल असं आयडियल मुलांना फायदेशीर होईल. मुलांच्या बऱ्याच रिक्वेस्ट दिसल्या मला चॅट बॉक्स मध्ये.
हा, हो, ओके. हे पेन टॅबलेट वर मी सध्या समोरच घेतलं, जे वाटलं
हो
ते.
हो हो,
आणि त्याच्यात
तरी पण
काही
त्याचं होत असेल.
ओके ओके,
सेव्ह
रायटिंग काही
करून-
बरोबर नाही तेवढी, पण ठीक आहे, इट्स ओके, नो प्रॉब्लेम.
नाही छान आहे सर, छान आहे. थँक्यू सर.